Today we will just try to understand what are the properties of central force. Properties of central force. And then we will go for a special case for a central force, and that special case is Kepler's potential. Kepler's potential. And after then, we will just try to go for basically three laws of Kepler's, that is Kepler's law. So Kepler's law is mainly for the Sun and Earth system, mainly for a planet and a star system where planet is revolving in an elliptical orbit. So we will just cover this particular thing into Kepler's law. We all know there are three different laws for Kepler, and we have Kepler's potential. That means we are just going to try to understand what is by nature of a different orbit when my potential is minus k by r. This is the potential is inversely proportional to distance between the two particles. So let's try to go for some basic property of central force, and we can also use all the concept which we have learned into last two classes, mainly the Newton's law in polar coordinate, and we will use all this concept to develop this particular topic. Okay, so let's try to go for first what is central force. So when I am talking about central force, I am talking about the force which will act between the distance between two particles, and that will act towards a center or towards a origin. What I am trying to say, suppose I have one charge here, and let's say this charge is at origin, and another charge is, let's say, Q2, and we can have this kind of situation. And the distance between Q1 and Q2 is, let's say, R. Let's say this is in XYZ plane or XYZ space. You can have something like this. And distance between them is R. Then force between Q1 and Q2 is proportional to 1 by R square. And if we are changing any angle, suppose I just shift this Q2 from this point to this point. Let's say this point is again Q2. Then I am just changing the angle. First, let's say this angle was θ1 and this angle was θ2, something like this charge in maybe XY plane. So what you will find, if this distance will same, then the magnitude of force will remain same. And yes, if there is attractive force, then it will towards the origin, and it will towards the origin. And if it will repulsive, then obviously it will something like this. It will just go like this. So force is towards a center. This is very interesting thing. So the force is towards the center, and if this kind of situation will occur, then we know this type of force is a central force. So one of the very beautiful example is the Coulomb's force. Another example is the gravitation force. You have two mass. Suppose I have a mass m1, and again I have mass m2, and the distance between them is, let's say, r. Let's say this is x and y. So this is r. So the force is nothing. You can identify this particular force is nothing but minus g m1 m2 upon r square. So this force is towards here. So you can assume something like this. Suppose you know that Earth is revolving about a sun. So suppose this is my sun and here is my Earth. So if I am talking about the force between sun and Earth, Even if its motion is along this direction, but force will act towards this. The force between sun and earth, the sun is just attracting all the planet towards itself. So this is your force. So you can assume this is your origin of the force and this is towards this. So why it is known as what? Central force. But you will surprise that motion of earth will be something like this. If you assume circular orbit or elliptical orbit, also that motion will be have, due to this particular force, there is change in angle. There is also change in, there is radial velocity as well as tangential velocity also there. So it's a very interesting. So we will discuss all this thing in a very deep manner. But before that, let us try to go for what is a basic nature of central force. What are the basic property behind the central force? What are the nature of the central force? So let's try to go for this. Okay. So obviously, if I am talking about force, this force can be defined as minus del V upon del R. In which direction? R cap direction. So force will be along the radial direction. This is in R cap direction. So if this is my force, then what will be my torque? Torque kya hoga? That is nothing but R cross F. And in a polar coordinate, even in a spherical polar coordinate I am talking about, in a polar coordinate, this R can be written as mod R cap cross minus del V upon del R cap. So R cap cross R cap, that means this value is equal to what? 0. So whenever you have central force, the torque acting on that particular particle is actually 0. So when this torque is equal to 0, what is meaning of that? Meaning of that, angular momentum of a system is going to conserve. And here I am taking angular momentum as a notation with J, because I will use L for other parameters. So here angular momentum is J and J is actually constant. So first thing what we have learned that the angular momentum of a system is going to conserve whenever your force is central in nature. So you can just go for angular momentum. Angular momentum of system is conserved. Angular momentum of system is conserved. Now, this is my first thing. And second thing, look at the next thing. When you will get R dot J, R is some radial vector. So let's try to calculate this particular element, R dot J. What is going to happen? What is J? What is J? R cross P. Very good. So that is nothing but R cross P. And you can write this thing as R cross R dot P. लिख सकते ना? With the help of a scalar triple product. Can we write this thing? So R cross R dot P is equal to, now what is R cross R? That is 0. So you can have 0. So now look at these two things together. The first thing is we have a very trivial situation that R dot J is equal to 0. And the another thing is that the J is going to constant. So if I am talking about J, that means I am talking about magnitude as well as in direction. So J as a vector is going to constant. And now if you will just try to see the whole thing in one frame, then what can be the conclusion? The conclusion is very interesting. You can see. Now, what is meaning of that from here? R dot j is equal to 0. What is meaning of that? Anyone?
R is perpendicular to J.
That means R is perpendicular to J. So whatever be the direction of J, R is going to perpendicular it, isn't it? So obviously if J will be in Z direction, then R will be in XY plane. If J will be in something like this direction, then R will be in this plane, isn't it? So you can just assume, suppose you can just assume that this pencil is the direction of J, and in this plane you have R, isn't it? And if this J is going to change, this whole plane is going to change, isn't it?
Yes, sir.
Okay, but look at what is going to happen. R is going to perpendicular, but J is constant. So if J is constant, so the direction of J is also not going to change. So what I can say the R vector is confined in a some particular plane where J is perpendicular to that particular plane, isn't it? The plane in which R is defined is not going to change. Why? Because J is not going to change. Are you people going to understand this particular thing? Everyone? Okay. So what I am trying to say, hence J is constant. Hence J is constant and R is perpendicular to J. I can say motion of a particle is confined in a plane, in a fixed plane actually, in a fixed plane where J is perpendicular to that plane. J is perpendicular to that plane. Everyone is comfortable up to this statement? This is very important statement.
Yes, sir.
Okay, good. So now this is our story. Now, if R is confined into one particular plane, then I can say that motion is confined into two-dimensional plane. Is that this statement is correct or false?
Yes, sir.
Yes, this statement is correct. So now look at here what we have done. We have started with a three-dimensional thing, and using the conservation law and the trivial equation that r dot j is equal to 0, using this thing, and finally we have concluded that we have to solve the central force problem only into two-dimensional plane. There is no need to go into three dimension, isn't it? And you will surprise more that we will do all the calculation into one dimension actually, but we will give the conclusion of the two-dimensional plane. So this is the beauty of formulation of central force problem. So here the motion is confined into two-dimensional plane. So when motion is confined into two-dimensional plane, how you will solve the equation of motion? You will use which equation of motion? Polar coordinate equation of motion, isn't it? We have learned into last class that if motion is confined into two-dimensional plane, the polar coordinate is the ultimate thing that you can solve the problem very efficiently. So what is going to happen? We have to solve this particular central force problem in a polar coordinate in a two-dimensional plane. So let's try to go for a solving central force problem in a polar coordinate, mainly in two-dimensional plane. Up to that, are you people okay?
Yes, sir.
Yes, sir.
Now, what is your equation of motion into two-dimensional plane? The equation of motion into two-dimensional plane is Fr is equal to m r double dot minus r theta dot square. Okay. And what is this particular Fr? This is Fr is equal to MAR. Basically, we have written this particular thing. Fr is equal to MAR. And from here, we know what is the force. The force can be defined as minus del V upon del R must be equal to, if V is the potential, then force is defined as minus del V upon del R, and that will be equal to M R double dot minus R theta dot square. Everyone is comfortable? And what about F theta? There is not any force in the direction of theta. So F theta is written as M A theta. F theta is actually 0 because force is central. So F theta is equal to 0. Then we have M R theta double dot plus 2 R dot theta dot. And from here, we can write d upon dt m r square theta dot must be equal to 0. In the last class, we have solved this thing. याद है ना? किया था इसे? And from here, we can easily say that this is nothing but the angular momentum, and this mr square theta dot is equal to constant. And let's say this constant value is equal to j. So what we have theta dot is equal to j upon mr square, where j is identified as angular momentum of a system. So this j is nothing but identified as what? And this is very important relation. This is very important relation. Why this relationship is so important? कोई बता सकते हो ये रिलेशनशिप क्यों इंपॉर्टेंट है? Anyone? Anyone? Why? Because you can see, if you are going to solve the problem into two-dimensional plane, then what is your variable? Your variable is r as well as theta. Yes? And theta dot you can easily replace with the r. So finally, what you can do? You can write each and everything in term of r. Something like this. Look at here. I am just giving you example. Suppose this Fr is written in which where you are using r double dot as well as theta dot. So here you are using two variables, but hence I can write theta dot is equal to j upon mr square. Then what we can do? We can write this all thing, this equation, I can write something like Fr is equal to m r double dot minus r, and what is this theta dot square is equal to j square m square r to the power 4. And this is nothing but the centripetal force, and this centripetal force can be written in a form of angular momentum, isn't it? And when you can write this particular thing, mr double dot minus j square upon m r cube, so Fr can be written something like this. So this is very interesting. So you can reduce the variable. Hence, we have one conservation principle. I can easily reduce the variable. This is very interesting. And you can easily solve the problem only in R, but you can give the justification for theta also. This is beauty of formulation of central force problem. Anyway, so first, so this is your, this equation and this equation is actually same. ये दोनों इक्वेशन क्या है? Exactly same equation. We will use these two equations simultaneously, depends on which kind of problem is asked in your exam. Now, if this theta dot is given, suppose this theta dot is equal to j upon mr square is there, then now look at, we can give a next conclusion. This is very interesting.
Sir,
Yes.
sir, in this FR new transform equation, there will be r to the power 4, na?
Why r to the power 4? This r and this r is cancel out one. This r.
Okay.
Okay. Okay. So this will be x and this will be y. Okay. This is your xy plane. And suppose in some time the angle swept by d theta at the theta angle. This is just swifting. This angle is d theta. So this is r and this is r d theta. Isn't it? I am just talking about this area. So what will be this area? So this area can be written as, you can assume for the small angle theta, this is just a perpendicular to this one. So you can just use half r into r d theta. Half base into height is the area of this particular triangle. And now if you are just going to divide with the time, so dA upon dt must be equal to half r square d theta upon dt. And what you will get? D theta upon dt, again you can go for j upon mr square. And this value is dA upon dt is equal to j upon 2m. Isn't it? And now you can see the same conservation of angular momentum can be written in a very different way. And that means your aerial velocity or aerial speed is much better. Aerial speed is constant. Aerial speed is constant. And you can see this is the also Kepler's second law, isn't it? Equal area will shift into equal time. That is not only for the Sun and Earth system. This is correct for each and every central force problem. This is correct for each and every central force problem. So second thing is that, and yes, in 1 year in the examination, it is also given that dA upon dt is conserved. That means angular momentum is conserved. Hence, angular momentum is conserved. Then only you can say dA upon dt is conserved. So Kepler just write the conservation of angular momentum in a term of area. That's it. Everyone is comfortable?
Yes, sir.
Okay. So now this is so what we have learned. So first thing we have learned, look at these all are the properties, and this the questions mainly in JAM examination can be asked straightforward. So first thing is that angular momentum is conserved. What is second thing? Motion is confined into plane. What is third one? Aerial speed is constant. And last and next term, you can see this force. You will just going to calculate what is the force. The force is basically radial force, and that is minus del V upon del R, r cap direction. And this force is not a function of time. The energy is not a function of time. So Fr, so if you are going to calculate del cross F, then this del cross F is also going to be 0. So hence your del cross F is going to 0. Then this force is known as what? Conservative force. Kaisa force hoga ye? Conservative force. You have learned this thing into your vector calculus, I think so. So F is identified as conservative. F is conservative force. Okay. Okay. So let's go for a next analysis. यहाँ तक clear है ना? Everyone?
Yes, sir.
Okay. This is very interesting topic. Very, very interesting. Okay. So let's go for a concept for circular orbit. Here I can discuss circular orbit. Let's go for circular orbit. We are just going to discuss circular orbit separately. So what will happen for circular orbit? So we have equation. So this FR is equal to M R double dot minus M R theta dot square, or you can write this thing as, you can write in term of potential also, minus del V upon del R is equal to M R double dot minus M R theta dot square. You can use this expression also. You can use this expression also. Minus del V upon del R must be equal to M R double dot minus J square upon MR cube. Isn't it? Both expressions are equivalent to each other. And let us assume R is equal to R naught is, let us assume R is equal to R naught is radius of circle. R is equal to R naught is what? Radius of circle. So for the circular orbit, radius is not going to change, isn't it? Radius is not going to change. When radius is not going to change, then R double dot at R is equal to R is equal to R naught, R dot must be equal to 0, as well as R double dot must be equal to 0 because the radius is fixed. So if radius is fixed, this thing is just going to happen. So now what will happen? Look at here. You have minus del V upon del R at R is equal to R naught must be equal to minus M R is equal to R naught is theta R naught, and I can write this thing is something omega square. And from here, this minus sign and this minus sign can be cancelled out. And what you will get? You will get the value of omega, or I can write it omega naught. The value of omega naught, this is nothing but the angular frequency or angular velocity, you can also say. We can easily calculate the what is value of angular velocity. And if you can calculate the what is value of angular velocity, you can easily calculate the time period also. And this is one of the very famous question for your examination. So what is going to happen? You will just get it del V upon del R at R is equal to R naught by M R naught. Yes, everyone is comfortable? So you can use this as a formula. And again, from here you can easily find the angular momentum. What will happen? Again at R is equal to R naught, R dot is equal to 0, R double dot is equal to 0. So again you have minus del V upon del R at R is equal to R naught. This term is going to 0. This term and this term is actually same. Both are centripetal force. So this will be minus J square upon M R naught cube. This minus is going to cancel out. And what you will get? You can easily get the value of J naught or J or angular momentum. That value is given by root under del V upon del R at R is equal to R naught into M into R naught cube. So you can find angular momentum, you can find your R naught, everything you can find. Suppose in some problem they will give you J, you can easily find the radius. But thing is that del V upon del R is, you have to calculate what is del V upon del R, and you can easily figure it out. What can be the angular velocity, what can be the angular momentum, or vice versa. They can give you the angular momentum, and then we have to find what is the relationship between the relationship for radius. And this type of question always came into your examination. So this is a very wonderful concept behind the circular orbit. But we all know that only circular orbit is the not a case. The orbit can be elliptical. The orbit can be your parabolic. Orbit can be hyperbolic. It can be bounded. It can be unbounded. So how we can tackle this sort of problem? So let's try to go for analysis of energy, and on the basis of that, we can easily calculate this type of, we can just qualitatively analyze which type of orbit can be there. At least we can say if orbit is bounded, whether it is circular or elliptical, or it is unbounded orbit. Up to that, everyone is comfortable?
Yes, sir.
ओके और
Yes, sir.
प्लीज जाकर इसे घर में रिवाइज कीजिएगा, है ना? जैम के 80% क्वेश्चन तो यहीं से बन जाएंगे आज की क्लास से, अगर आप जाकर प्रीवियस ईयर क्वेश्चंस को अटेम्प्ट करोगे तो। Okay, so let's try to write the expression of energy. So let's go for energy analysis. Okay, so what is energy? In two-dimensional, we have energy E is equal to half m r dot square. This is nothing but the translation kinetic energy, plus we have half m r square theta dot square. This is nothing but the rotational kinetic energy. You remember what is your V? V in a polar coordinate is r dot r cap plus r theta dot theta cap. You remember all this thing? So this is my kinetic energy, as well as we have potential energy. This is my potential energy. And you can see this energy is not a function of time. So if you are going to calculate dE upon dt, that equal to 0, that means your energy is conserved. So your energy is going to conserve. This is all about dE upon dt is equal to 0. So energy is going to conserve. And we have also this particular formula or this particular expression that theta dot is nothing but J upon mr square. Everyone is comfortable? Theta dot is nothing but what? J upon mr square. If theta dot is J upon mr square, now look at here. We have translation kinetic energy, we have rotational kinetic energy. So this is our translation kinetic energy. This is our rotational kinetic energy, plus this is our potential energy. So you can write it PE. This is our potential energy. So what is going to happen? Just we are putting this particular value theta dot is equal to j upon mr square. Then what I will get? I will get E is equal to half m r dot square j square upon 2 mr square plus Vr. Everyone is comfortable? And now you
Yes, sir.
can see, hence theta dot is j by mr square. Again, what we have done, we have removed one variable theta dot as a function of r, and this energy is only written as a function of r. R is the only variable. Obviously, time is important part because the system is dynamical, so time will be always there. But look at here. This is your total energy, and this is nothing but the rotational kinetic energy. We have just written rotational kinetic energy as a function of r by replacing theta dot. And what I will get? I will get these two things. Now, if someone will just join class at this particular time, and if I will ask him that what is your kinetic energy and what is your potential energy, then obviously he will confuse and he will say, okay, this is my kinetic energy. And the whole thing is, this is also function of r, this is also function of r, then whole thing can be treated as potential energy, isn't it? Because for the kinetic energy, you need to go for velocity square. But here we can give this particular term as known as E is equal to translation kinetic energy. This is translation kinetic energy plus V effective. And this V effective is, this is V effective, and this V effective is J square upon 2mr square plus Vr. This is your effective potential energy. So what you have when you have central force problem, only potential energy will not decide which kind of orbit is there, what are the nature of orbit, but you will surprise that potential energy plus rotational kinetic energy as a function of only r can be defined as a V effective will decide which type of orbit can be there. Okay? यहां तक किसी को कुछ पूछना है तो पूछ सकते हो. Then we will go for analysis of V effective. Okay, so let's go for analysis of V effective. So this is a last part. We are just going to cover analysis of V effective. Okay. So this is just we are going to plot V effective versus R. And let us assume there is some hypothetical plot, but for each and every potential, you have to plot V effective. We will discuss this type of problem in next class, but we are just going to deal it qualitatively. So what is going to happen? Suppose let us assume this type of potential is there. This is one of the just hypothetical potential. Suppose your potential is there. I deliberately chosen this type of potential because I can discuss all type of motion here. Okay. And suppose we have this much of energy. Suppose my particle have this much of energy. Let's say this energy is E1. This region is what? Classical forbidden region. Everyone is comfortable? Yes or no?
Yes, sir.
Yes. Total energy is less than potential energy, so it is classical forbidden region. This point is known as turning point. So your particle will be remain into this region. So this is bounded or unbounded? Just tell me.
Unbounded.
This is unbounded. So this region is unbounded. So if it is unbounded, which kind of orbit you can have? Either parabola or hyperbolic, isn't it? These are unbounded orbit. Now, so this for this kind of, if this kind of situation is there, okay, let us assume this is your turning point for this particular energy E1. Okay, let's try to go for this energy. This is very interesting. This is very interesting. I am just denoted at E0 for this. E0. At this, is that this is minima of a curve, isn't it? Everyone.
Yes, sir.
This is
Yes,
minima of a curve.
Yes, sir.
Okay. So what is meaning of minima of a curve? If we are going for del V effective upon del R, that must be equal to 0. Because this curve is built between V effective versus R. So del V effective upon del R is equal to 0, as well as del square V effective upon del R square at some particular R is equal to R naught. This is your R naught. At some particular R is equal to R naught. This term must be greater than 0. This is condition of minima.
Yes, sir.
Yes. Now look at what you are getting from here. Look at. What is your V effective? V effective is nothing but J square upon 2mR square plus VR, isn't it? And let us try to go for del V effective for del R by del R. At which point? R is equal to R naught, isn't it? That must equal to 0. So if we are going to differentiate it, what is this value? J square upon mR cube minus sign will be there plus del V upon del R must be equal to 0. At which point? At R is equal to R naught. So what you will get? You will get minus J square upon m R naught cube must be equal to minus del V upon del R at R is equal to R naught, and this minus will cancel. You have J square m R naught cube must be equal to del V upon del R at R is equal to R naught. So what is this condition? अभी देखा है आपने ऐसा कंडीशन? क्या कंडीशन है ये?
Circular motion.
Circular orbit, yes. And what is this R naught? This R naught is also minima mathematically, but this R naught is identified as what? Radius of a circle. Okay. And now, so for this particular energy, if your particle is confined here, then you have which kind of orbit? Circular in nature. And this R naught is, you can say it, this is minima of a curve. Minima of V effective, you can say, or radius of circle. Everyone is comfortable? So this is something like grid, and you can see there is only one, and this is something like bounded curve. So you have circular in nature. So for E is equal to E naught, if you have this type of situation, this is also known as circular. This is condition of circular orbit. And yes, if this thing is again going to hold, then R naught is also identified as a stable equilibrium point, isn't it? Stable equilibrium point. What is condition of a stable equilibrium point? For the stable equilibrium point, that should be the point must be what? अभी हम लोगों ने minima of a curve, and that is, and if you are just plotting this particular V effective, so this R naught is identified as, so this R naught have two significance. One is it is identified as radius of circle, and second thing, it is also equivalent to what? Stable equilibrium point. Yes or no?
Yes, sir.
Yes. And this is again classical forbidden region. And what about this region? Is bounded or unbounded?
Unbounded.
Unbounded. If your particle is in this region, you have unbounded. Okay. So this E naught is very interesting. Okay. Let's try to go for this level of energy. This is very interesting. Let's say this is E2. This is E2. And now this is your forbidden region. There is not any problem. This is bounded or unbounded? Here, this region?
Unbounded.
Unbounded. Very good. And what about this 2 point? This is your classical allowed region? Yes?
Yes, sir.
Okay. And this thing can be written as R minimum. And this thing can be written as R maximum. And R is varying between R minimum and R maximum, isn't it? So this orbit is bounded or unbounded?
Bounded orbit.
Bounded orbit. So this is your bounded orbit. So if this is your bounded orbit, which kind of orbit can be there? ऐसा कौन सा ऑर्बिट होता है जिसमें R की वैल्यू दो वैल्यू के बीच में फिक्स होती है?
Circular or
Elliptical in nature. Elliptical in nature, isn't it? So if your particle is bounded into this region, then this is elliptical in nature. So this is an elliptical between R minimum and R maximum. So this is your elliptical orbit. And now, if you will see this figure very carefully, and you can just go for my class of stability analysis. I am just using this thing, this place. Suppose this kind of thing is there. This is basically V effective versus R. This value is R minimum. This value is
R maximum.
R maximum. Is that R minimum and R maximum is turning point?
Yes, sir.
Yes. So what will happen to turning point? At R minimum and R maximum, R dot is equal to what? 0?
0.
Isn't it? So linear velocity at the turning point is going to 0. That is one more information. You should remember this thing. And now this point is what? A stable equilibrium point? R naught को क्या कहा है? Stable equilibrium point?
Yes, sir.
है ना? ये वाला point, ये जो point. This is your stable equilibrium point. And now if your particle is bounded motion about a stable equilibrium point, which type of motion can be analyzed like this? किस तरह का motion आप कह सकते हो इसे?
Harmonic
just
oscillator.
oscillatory motion. Very good. So this is equivalent to oscillatory motion. And if it is equivalent to oscillatory motion, for the small oscillation, what should be the angular frequency? And let's say this is, I am writing omega e for the elliptical. What should be the angular frequency for the small oscillation?
Under root del square V by del X.
Del square V effective, isn't it? By del R square at R is equal to R naught.
By A.
R is equal to R naught by M. This is very interesting thing. So now you can see how we can use stability analysis in this particular topic, isn't it?
Yes, sir.
कितना important topic है? Small oscillation में भी use हो जा रहा है, यहाँ भी use हो जा रहा है. Whenever you have motion about a stable equilibrium point, and if you want to go for the harmonic oscillator, something like you can get this particular thing. So this is very interesting. If you have elliptical orbit, you can compare it in a one dimension, it is just oscillatory motion. But in a 2 dimension, it will look like an elliptical orbit, isn't it?
Yes, sir.
And now look at how beautiful is this analysis, effective analysis for the effective potential. You are doing analysis into 1 dimension, isn't it? This is V effective versus R. But you are giving the conclusion for what? 2-dimensional plane, isn't it? हाँ या ना?
Yes, sir.
भाई ellipse, circle, कैसा है? 2-dimension plane का orbit है? Yes?
Yes, sir.
Okay. And last but not the least, if I have this sort of orbit, you have bounded or unbounded?
Unbounded.
Unbounded. Okay. So this is all about the qualitative analysis of your effective potential. I am just giving you one homework. I will just start next class from this particular problem. But before that, you have to do little bit of mind storming for this particular problem. और अगर आपसे solve होता है तो आप solve करके भी भेज सकते हो. Okay? Everyone is comfortable?
Yes, sir.
Okay.
Yes, sir.
Good. So just go and revise this thing very nicely. In your study material, it is given very nicely. Everything is given point wise. Okay. So just try to go for this. Okay. And if you are confused, then ask me doubt. I will clear it. Okay. But try to revise it very carefully, because every problem will come from this part. Okay. Let's try to go for one particular homework problem. I will solve it tomorrow. If VR is given by half kr square, J is angular momentum, and it is given, and m is mass of a particle. First, plot V effective versus R. Second, find the radius, energy, and angular frequency for circular orbit. And third, if energy is slightly changed, if energy is slightly changed, then what will be nature of orbit? And for elliptical orbit, find omega. Okay. Just try to do the with yourself. बुकलेट देखने की जरूरत नहीं है क्योंकि बुकलेट में भी सॉल्व है. So don't try to see it. Just try to do with yourself whatever we have learned today. Just revise your copy and then try to solve this problem. But in next class, I will surely solve this problem. I will start from this part. So next class, we will start from here and then we will go for a differential equation of one or two more problem. Then we will go for differential equation of orbit and we will analyze Kepler's problem. Okay. V is equal to minus K by R. ठीक है?
Yes, sir.
चलो,
Yes, sir.
take care. Thank you.
Thank you, sir.
Thank you, sir.